Okay, so it's a pleasure to have Taşkın. He's both a MIT alumni and an old friend. So it's been quite a while that he's here, and it's good to have him here. I'll just read his bio. You can see that he's a graduate of electrical engineering in '93. So he put that up here, not in the bio though. So he holds concurrent appointments as a professor of electrical and computer engineering at Northeastern University in the US and an Amazon Scholar. He's the director of the Robotics and Intelligent Vehicles Research Lab. His work focuses on advanced robotics, including shared autonomy, human-in-the-loop robotics, collaborative robotics, embodied AI, and human-robot teaming for applications including disaster response, personalized care, and manufacturing. So without further ado, it's a pleasure to have him here.
Thank you so much, Errol. Thank you. Sorry about the little hiccup we had before we started. This was long overdue. As Errol mentioned, I've been watching how ROMER, was founded, and then it evolved. And it happened that I was around this week, and I'm delighted to be here and to talk about some of the work that we've done in the past decade and some. And then I also want to give you a projection to what I will be working on. Maybe that will inspire some new thoughts for you as well. The title of the talk is Experiential Robotics for the Future of Work. As you age, your slides become more visuals, more videos, and your titles become more, jazzy than technical, but I also have some deep dives that we want to go. Let me first address the elephant in the room. What is experiential robotics? This is a term that I've been using for more than 5 years now, and I describe it using 4 elements of experiential robotics. First, it's robotics to enhance human experiences, at all aspects of life. We'll come back to some of the individuals that you see here, but whatever it takes, we design and develop robots to enhance human experiences. If a robot is not helpful for a human, why are we even working on it, right? So that's the first element of experiential robotics. The second element is you also see the age of the presenter if you put down your declined proposals on your slides, right? So this was my career proposal to the National Science Foundation. I called it personalization of assistive robot control, about a little bit more than 10 years ago. But the idea here was when you purchase your smartphone, the first thing that you do is you start personalizing it, right? So there are no 2 phones that are exactly the same on the universe, in my opinion, correct? So we cannot design one robot that will fit all our needs, right? So especially if we want to interact with those robots, if we want to collaborate with those robots, etc. Embodied AI, I use this term very cautiously when in my presentations. I did not train as an AI expert, but we use machine learning, we use artificial intelligence in our work as it applies to as it supports the other 3 elements of the experiential robotics. I'm showing you, Rod Brooks' seminal work on intelligence without representation, where he spun off the embodied cognition term. In my opinion, if there's a meaningful way to use embodied AI, we should use it. Then the 4th element is you cannot be in your labs and imagine that, hey, I'm going to design this robot and then it's going to help somebody, right? So this is me and, not my students actually, 2 postdocs and a PhD student. We did not dress up to enter a surgery room. We put the PP on because we were walking into a lobster processing house. It was a very small manufacturing of seafood manufacturer, to see their operations. Now, you may wonder, how did we go from robotics to seafood? The first set of, here's your summary. The first set of, before I that, so experiential AI, experiential robotics, as a term I spun off, again, 5+ years ago. And then at Northeastern University, we launched our Institute for Experiential Robotics, very much similar to what ROMER is trying to do, provide an umbrella organization for our faculty, for our students. We have 5 areas of research that we put ourselves into, but then at the center, how do we enrich the human experiences through meaningful deployment of robotics? The first set of projects that I'm going to talk about, so the title is Exponential Robotics for the Future of Work. So what is the future of work? And hopefully you'll get to see some of the elements. So this is the CRISP project. We got this funded first from the Department of Defense in the U.S. and then the National Science Foundation. In the U.S., you may not know this, there is a trade deficit in seafood, about $20 billion a year. So that means U.S. buys more seafood than selling, but then that doesn't make sense because the U.S. is next to two big oceans. There's Alaska where all the whitefish is caught. So when we dug deep into this problem, we realized that what happens is, for example, in Alaska, they catch metric tons of whitefish. It got shipped to Asian countries for processing, and then they clean it, they process it, and then they create these blocks of whitefish. And then U.S. buys it back for McDonald's fish fillets and things like that, right? So that fish traveled far away, came back. So it didn't make sense. So what we did was we took that problem and then we had a pretty. So one thing I want to mention, I'm the only engineer in this team. So we had an interaction design, we have an labor economics expert, we have an ethics expert, and then we have a workforce development expert. Because in the U.S. you cannot just say that we will introduce automation, everybody starts waving their hands and then say, what about the jobs, right? So, we had to look at the problem from all aspects. We imagined this factory of the future. I don't want you to read the nitty-gritty details. This was during the COVID, by the way, when we did this study. Things changed quite a bit at that point. One thing that I want to point out is that we always talk about Industry 4.0, seafood Industry 4.0. We are probably right around this 1.1 level in many operations when it comes to these underserved industries. I'm sure if you go to any industrial region in Turkey, you will find out that most of the things that are done there very labor intensive. There's literally no technology, and in the U.S., one problem is the sustainability of the operations because there's an aging population, and that one guy who knows how to do X is going to retire in the next 5 years, and then there's no one who knows how to do it. So we created a roadmap, and then we saw things like this. So I'll show you a few projects that we completed under this program. So this is a seafood processing plant in Portland, Maine. It's a very small place. And then workers all day long, they unbox these frozen fish. And then that frozen fish goes into that big machine where it gets defrosted just to the right amount so that they can process it, and then they freeze it and then put it into market. This is called added value, right? So sometimes added value is just portioning it because, guess what? Americans don't like to buy whole fish and clean it in their homes. They want to buy the little fillet and then process. So then we asked the question, what can we do? So this project we labeled as, we called productive inconvenience. If your job is to move these 7.5 kilogram boxes all day long, you're prone to safety, right? So you will have injuries at the end of the day, at the end of the week, at the end of the month. So one idea is that can we introduce variability into the human-robot collaboration? What that means is that you don't just go and pick up the box from the pallet. We have a collaborative robot arm that presents the box at a given region, but then we played with that region. We said, okay, so it can be assistive, right? So every one of us has our golden zone, right? So I feel comfortable picking a box at this pose, but then that also becomes a repetitive task, right? So I always go to that location, that position. Can we introduce an assistive one? So by following all the ergonomics literature and aspects, but then can we also do stimulating one? Now I'll share with you how the stimulating concept came about. If you work for a tech company, or if you work for a startup, you can during the day you can take half an hour or an hour to go to the gym and exercise, right? So this is pretty common. Now, if you're working for a seafood processing company, that's not an option, right? So you're worrying, you have other worries. So this was, in a sense, can we introduce some stimulating motions for the workers so that they feel more engaged with the task, and then they feel and perhaps there's a path to minimize the injuries. So we did. Again, during COVID, you can tell from my students, masks and all that. During COVID, we completed this study, and then we looked at the assistive, we looked at the stimulating. I mean, both videos look alike, but then what's happening is that on my left, in the stimulating, we present the box outside of the body of support, polygon of support for the workers. So that person needs to do something a little bit different. And then in the other one, we are tracking where the workers is standing and then presenting at the most ergonomic pose. Before I go into the results, I have one more slide. I want to point out that I never did during my PhD, I never thought that I would write a paper in the transactions on occupational ergonomics and human factors. But this is the power of a multidisciplinary research. This is where we published this paper, and then surely enough, our results again from the human study that we did showed with the stimulating there was some advantages that you gain, and it was well received. Okay, moving on. I'll bore you with seafood a little bit, but then we'll go into some of the other projects. We visited another place, and then we saw this. So this gentleman is pretty wealthy because this gentleman knows how to process a 275-pound swordfish or tuna fish. You may wonder, what about it? What this fish? Every little bit of meat that you leave on the bone or that you leave on the skin is waste from the company's perspective, right? So when these persons, when these workers are trained, oh, by the way, there are not a lot of them. We heard, again, don't quote me on this, but we heard that it takes about 18 months for someone to get trained on how to do this right. And then there was only 1 or 2 people in the greater Boston area. And guess what? Boston is right on the ocean. And then they cycle from company to company. And then the idea here was, okay, if there was a robotic system around this, right? So there was a coworker robot around this, not to replace this gentleman because there's we know the challenges of robotics, but then can we shave off a minute or 10 minutes or a half an hour through the collaboration? Can we help this worker to do their job faster and quicker? So what we did was, this is where the interaction design piece came in. So one of our experts looked at what do they do, right? So there's regions on the table. They first pull the big piece. They make a big incision. Again, I'm just giving you the idea. But then we created a catalog of tasks where, I push this big piece out and then, I'm done with this. It needs to go away. But then every push, every touch is the worker's is time on the worker's clock. So we said, okay, so what if there was a robot that's not, again, this is a prototype definitely, but what if there was a robot that's not a robot arm, that's not a robot, a humanoid, obviously. What if the table is a robot, right? So we created this concept of voxel-enabled robotic assistant. What it is that, your tabletop, it's not a conveyor belt because conveyor belts they go in one dimension, maybe 2, but you cannot pack them in systems. So in the prototype we did 2 16 voxel tabletops, but then it's modular, right? So you can go from 16s to 4s to 1s, in one form or shape. And then we demonstrated that, hey, while I'm doing the cut, while I'm doing the important work, we can literally transport things on top of the table on top of my workspace, right? So my workspace is my robot coworker, and then we can take things away. We can bring things to you as you focus on the most important thing. So we published this at IROS last year, and again, like any other prototype, now it waits its time to, how do we make this refined? How do we take this to the next level and whatnot? Part of our work in the past, again, with one PhD student, I always say no champion, no project, no exceptions. So every PhD student comes in with an idea and we say, okay, let's see what we can do. One of my students was very enthusiastic about hyperspectral imaging. And we said, okay, so we've seen so many automation meaning there's a conveyor belt coming, and then workers are looking for shells in scallops, let's say, or shrimp, right? So they're seeing if there's something that doesn't fit. So we created a gripper. More than the gripper, the sensing suite around it can look at the workspace, not in the visible light spectrum, but in the invisible light spectrum. And all of a sudden, all your anomalies light up. Okay, so this was a quick way of demonstrating the case that if you're looking for something that doesn't fit with the product that you're developing, you can perhaps you should look in the invisible light versus the visible light. One last piece, I think, on the seafood, and as we were coming to the end, is this running? So it's running here, but it's not running there. Well, you can look at it because this is on YouTube. We created a chopstick-inspired robot end effector. If you're following what's happening at the, in robotics these days, everyone is trying to build hands, right? So, there's maybe 50 companies, they're trying to build, dexterous robot hands. But then we use tools with our hands. I'm not advocating that, dexterous robot hands will use chopsticks, but then if chopsticks are useful for something, oh, by the way, for centuries, chopsticks are used for, feeding, cooking, etc. The motivation for us here was, my video is running here beautifully. I'm watching the video, but hopefully you'll visit the YouTube video. One thing that we heard for top quality seafood, you're not supposed to touch it, right? So if in the U.S. scallops or in a really good quality seafood, so or minimizing the touch. So rather than hands, hey, two tips perhaps is good for that purpose. So I'll pass on. All right. So experiential robotics, and then I showed you a bunch of things that we've done in the seafood industry. That project ended about a year or so ago, but then there's now a new initiative, a very large consortium in the New England, and we are one of the finalists for a substantial award from the National Science Foundation to translate all the research findings or the research outcomes we had. Now I'm going to talk about avatars a little bit. This was a project. Let's see if this is going to run. Okay, perfect. This was a project. This was a side project. You're working on your papers. You're working on, hey, we are going to do manipulation. We are going to do teleoperation. We will build these actuators, robot hands, and so on. Right at the same time, X Prize, if you're familiar with the organization, X Prize had this space-themed avatars concept, right? So the idea is it's not about the robot, but the robot is in between. It's a human to human interaction or human to environment interaction. And the theme was space. Now, it wasn't the first time this theme has been used. DARPA Robotics Challenge was the disaster response, and then NASA came in and, with the Valkyrie program, that was space exploration. But here, there's the space station where you got to do a bunch of tasks, right? So, by the way, the operator is a novice operator, so it's a judge. And we had only 30 minutes to train the judge on how to use the system. and then in this case Peggy, she goes and utilizes the system to do things like, okay, grab a hand tool and then unscrew the screw, and what will come after this. And you've seen, I picked bottles, water bottles. They represent, fuel, but then one of them was full, the rest was empty. So find a, heavy one and then put it in, etc. So the idea here is it's not just one-dimensional teleoperation. There's the bidirectional, right? So you're going to provide the haptic feedback to the operator. Now this is where the video gets boring, because we spend almost 10 minutes to reach in that curtain and touch the rock with the rough surface and then pull it. And then somehow she kept pulling the curtain, but not the rock. Eventually she did, and then here's what happened at the end. So we ranked the third, the best team in the US. Nimro was from Germany, Poland Robotics is from France, and we came in third. Students were happy because they won $1 million out of this. But I want to talk about why this is important. I'm not going to talk about DARPA Robotics Challenge. I'm going to talk about a little bit NASA program that we worked on. If you remember DARPA Robotics Challenge, the finals were in 2015. Okay, it's 10 years ago. Go back to Urban Challenge, which was the self-driving cars. 10 years fast forward, we ended up with lots of self-driving car companies, and then now there are, there was some down selection, and now there's really a few strong ones who are deploying robotaxis and so on and so forth in big cities in the US. So DARPA programs has this 10-year life cycle before something becomes really trendy, let's say. DARPA Robotics Challenge was about humanoids, and it was the Boston Dynamics Atlas that we worked on, and then NASA Valkyrie, and then currently, oh boy, do we have a trend in humanoid robotics, right? So in all forms and shape, small or big, etc. But everyone is pushing for full autonomy. While they are teleoperating their humanoids for data collection, for creating that foundation model for policy, etc., etc. Avatar X-Prize happened 5 years ago. My take on this, and then maybe in a few years we meet again, and then you can keep me accountable on this claim. This is a claim, by the way. That in a few years we will see the advent of this avatars to provide remote work, because we will have reliable hardware, but then they won't be able to do to the level that, hey, autonomously I'm going to walk in and then I'm going to do all these great things at work. So there will be someone, maybe it will be a one-to-many paradigm, but then someone will supervise, will guide, and then will help robots to perform their job. Okay, so while I was speaking, I assume that you read the slide. So we had a very complex system, by the way. The reason for the complex system was my collaborator, Professor Whitney, works on this hydraulic haptic system. What it is that, it's something that we all did when we were little. You have a piece of hose, you fill it up with water, and then whatever you apply here, you can feel it there, right? So, he has that pressurized pneumatic lines, which really provides almost one-to-one haptic feedback to the operator. That's how we were able to detect, if this is heavy or if this is the rough rock versus the other one. So I'll pass some of these, but I want to show through the avatars we were able to complete some really neat and complex tasks, right? So, and this is again pre the diffusion policy era, if you think about it. Diffusion policy came about a couple years ago, but then we had this teleoperation system where we can complete these tasks and collect not only vision data but also haptic data, which is, in my opinion, very critical, because you can change the shape and size of this rope, then that basket weaving task becomes totally different for the robot. I won't be able to show it today because it's fairly new. Peter completed a full upgrade of the system. We now have a modernized way of, let's say, a modernized version of this avatar for data collection in the physical world for tasks like handling high consequence materials, etc. Okay, in my opinion, avatars will come in handy, not only space exploration, not only manufacturing, but also in many health-related tasks. I think this is a worldwide global problem that experts are not where you are. Okay, so your doctors, your medical experts are not where you are, meaning we got to provide them with tools to remotely provide care. I will quickly talk about this Valkyrie program because I wanna show you. Again, I made the case that AI is good, but then if it is meaningful, if it is if it helps, it should be there. So I'll show you a number of a number of projects where we use AI or machine learning. So this was a program that followed the DARPA Robotics Challenge. MIT and Northeastern received one of each of these robots, and I graduated 3 PhD students because it's a cool system. It's a system. It's a highly complex system, and it was the best of its class in my opinion in terms of the hardware during the time that we worked on it. And then we completed tasks like turning valves and picking up things, etc. It had dexterous hands, 4-fingered hands with tactile sensor. Really neat concept, really well built. However, they were so fragile. Anytime you make a lateral force contact, you break a tendon. I say this when we worked on Atlas, Boston Dynamics, we bought a bucket and a mop into the lab because it's hydraulic, it leaks, right? So we were wiping oil from the floors. When we had the Valkyrie, we bought a sewing kit so that we can fix the hands, so after a while, it just became too much of a burden. Anyway, right at the same time, we also worked with the Department of Energy, where we looked at constrained motions, because the idea was, we have all these nuclear waste. Well, US has all these nuclear waste in their old buildings, old facilities, and somebody has to go and clean it up because they are a burden on the generations to come. And in many of those facilities, there are glove boxes. And those glove boxes, you got to, where you make the scientific experiments, right? You put your arms in, etc. So my postdoc and my PhD student worked on how can we really design trajectories so that the robot at least can go in and then do certain things. So I want to go a little bit into, I didn't want to have just videos and pictures. Some equations are on the way. So we created this contact trajectory optimization framework, which solved a non-convex, nonlinear problem through successive convexification. So the idea is, so we don't want to plan everything, right? So because the idea is, I need to clear things, right? So sometimes we just push things, shovel things into big bags, right? So if you're trying to clean up waste. So the idea is that there's no one world we should literally one by one plan those things. Can we find contact-rich motions? You have a high-level task, clear the tabletop or empty the glove box, and then how can we achieve this? Now, again, if you follow the literature, a lot of people work on pushing within the context of robotics. We are still working on pushing within the context of robotics because it's hard for a number of reasons. And one is contacts, rigid contacts are challenging because you don't know how the objects will behave, right? So you cannot really model. So the first thing that we did was we created this contact model, published at IROS, and then the idea there was, it's a simulation, it's a model, but then using this, we created this contact implicit trajectory optimization. what's happening is we are not telling the robot to push this red box, at this point. The task is to kick the blue box. We bring the objects. We have the understanding of the scene. We bring the objects dynamics into the model, and then robot figures out where to make contact and then how to create the trajectory so that it can complete the task. So for those of you who are interested in robot dynamics, model-based robotics, we all know that our models are nonlinear. They are highly complex. And really, we can deal with nonlinear models, but then solving them real time while we are performing the tasks, it can become computationally challenging. This idea of successive convexification actually is first proposed by Professor Açık Meşe from University of Washington. He used this in the context of neurons, but this was the first work that I could, my student, used it within the context of manipulation. And the idea is you can successively convexify, as the name implies, your problem by linearizing your models over a trajectory. And then you continuously solve for your trajectories, and voila, you achieve your results. So we did some pushing, etc. And then, of course, there has to be a fish because this project overlapped with it. We did all this work on prosthetics. I'm going to skip all of these because this is going to take long. I want to get to the next 5 years because this is more for me actually, because I want to motivate myself, for the next 5 years and what I want to do. Extremes, right? We use it. Oh my God, this is an extreme situation. So extremes this, extremes that. But then, with a few colleagues, we came up with a definition where we can operationalize, right? So here's what I mean. So extremes are high consequence operations. So there's a lot at stakes, right? If you're putting a rover on the moon, it's a high consequence application, right? So you don't want your rover to fail. Or, by the same token, if I want a robot to provide care to my mother, right? So that's a high consequence operation that are inherently and unavoidably hazardous and occur under harsh environmental conditions, such a car accident, at the limits of human abilities. One morning you wake up, you're happy, you are driving your self-driving vehicle, you're in your self-driving vehicle, and then your interactions will be different. But then if you're late to work, if you're late to a meeting and there's traffic, your interactions will be different. Human-robot teaming, and if you notice, I didn't say interaction. Teaming has two agents, human and the robot, so they need to co-adapt, or both. Okay, so we defined this, but then we said, okay, a definition is a definition. What are some characteristics of an extreme? What are some of the knobs that we can up and down? A common question that I get from my students, my current students or prospective students today is, okay, so and so published this paper, this is done, how am I going to finish my PhD? Or what will my PhD research be? And I said, I'm going to give you 4 knobs. You can dial up and down, and you will find your problem. So problems won't change. So those 4 knobs are, VUCA. Actually, this is a I came across this about a few years ago. This is a training model that the U.S. Army uses for their officers. So they describe events in terms of their volatility, uncertainty, complexity, and ambiguity. So human-robot teaming, dynamic and improvised, right? Next time you empty your dishwasher or whatever your favorite chore is, look how much improvisation you add. So from yesterday to today, it's different, right? And it's dynamic. How many times do you collide with? There's no one world, the robots will avoid all obstacles because humans don't avoid all obstacles. I've been making contacts with the table, as I'm presenting, for example, right? So dynamic and improvised. Unpredictable, meaning uncertainty. Anytime you put the sensor, whatever, however much you pay, that sensor will have uncertainty. It's on your hands. Can I just go with a cheaper sensor and then I have more uncertainty? All of a sudden, all that beautiful published paper results come down. So uncertainty, complexity, multidimensional, multimodal, and hazardous. That's where the extremes come into picture. And then confused in cause and effect, which is ambiguous. You can have the beautiful autonomous robot and then put it next to my wife, in the kitchen. The instructions, the conversations, the ambiguity will be there, right? So, anytime you bring in that teaming aspect. So what I tell my students, and maybe this is a take-home message for some of you who are pursuing your programs, up these up. You don't have to do all at one, right? So you say, okay, I read this paper, they made this assumption. Oh, by the way, they assume this band of uncertainty. What do I gain? Or what can I do if I allow more uncertainty? Or more interestingly, dynamic and improvise, right? So volatility. If you don't believe me, Harvard Business Review has a paper on this, VUCA guidelines, categories. Read it. It's an interesting read. No technical terms, but it has been guiding our research, and I think it's good. So in the next 5 years, I want to start from the end. I don't want to start on a problem where I can solve, okay, if I do this, I can get to this paper. If I do this, I can get to this paper. No. I want to start from the end, meaning we want to solve a hard problem at the extremes. A firefighting robot in a car crash scene, right? So now roll back, right? So start rolling back. What can we do? This is still, far away, but work in the extremes. While you're working towards the extremes, you'll have discoveries, and then probably they'll be faster. I'll give you one or two examples given the time. This is our recently published RAL paper. It's a quadruped. There are plenty, and our spice here was uncertainty. Let's bump up the uncertainty. What did we do? We added 6 kg of weight onto the robot, and we said robot doesn't know about that, right? So robot model did not account for that 6 kilograms. We also moved the robot on any terrain. Robot didn't know about. What we did was, what my student, I shouldn't say, Ananya and Sarvesh, what they did was, what matters? How do we provide stability and locomotion with the contacts with the ground, right? So robot has to take steps. So you can plan steps, but then if you have all these uncertainties, if you have all these unknowns in your model, you're likely to fail. What they did was they modeled the friction cone between the robot's feet and the surface using a chance constraint convex MPC. So we added the uncertainties at that friction cone. Again, you can solve this because it's a convex MPC problem. You treat the robot as if it's a single mass, but then in these demos, what's impressive, again, I take a look at the paper. It's just got published. What's impressive is that we added significant. It's more than 50% of the weight of the robot, so that it can still go. This is not going to run, so I'm going to pass. One other thing is we just completed the full fitting of our off-road vehicle. So this is a full-size ATV that can be human-driven or it can be autonomous. There's an autonomy stack. There is an advanced sensing system, which I talked about a little bit. So we used the hyperspectral imaging. We created an outdoor version of it. And then we published quite a bit of papers. You may wonder why, right? So we upped the uncertainty or even the volatility. You can look at mud, right? And then your RGB cameras may say, okay, it's mud, right? We can do that. But then how do you know if you're going to sink or you can go through, right? It's usually not until you are in there and then you're in trouble, right? So what we did, especially in the last piece, this is again yet another RAL paper that just got published a couple months ago. We trained a model where we look at mud. So in those boxes there's soil, but then we have been adjusting the water level. So one is more muddy than the other. And then we train this this machine learning algorithm where now we can look at the scene. You have your visual scene, but then your mud appears as mud to your RGB camera. Your hyperspectral cameras can pick it up as this is 50% water content versus 10% water content. So that allows us to make the decision, can we traverse or not? Okay, last piece, because this is the latest and to me greatest. I've done work on smart wheelchairs, smart robot arms, again, 15 years ago. That was the very first National Science Foundation project that I took. This is Owen, one of our collaborators, and we took this video the beginning of this month in Pittsburgh. University of Pittsburgh just secured a fairly large funding from the ARPA-H. ARPA-H is NIH's DARPA equivalent in a sense. So ARPA stands for Advanced Research Projects Agency. H is health. So the idea here is for the next 5 years, we'll work on RAMP, we call it, robotic assistance, mobility and manipulation platform to provide independence for individuals with disabilities. But I don't want you to think about disability as a physical disability or a cognitive disability. As we age, as we get older, I may need a platform that will take me from my home, from my apartment to the corner store so that I can buy my groceries and then come back home, right? I may be pretty mobile in my home, but that, come down 11 flights to the first floor and then get to the market, coming back up, maybe too much. So can we have a system that can provide this? So what you're seeing here as I'm talking, this is our very first demonstration that we will have in May. Owen is pretty tech savvy, as you can tell. He has one of those quinoa arms. He can teleoperate it. Through his personalized interaction devices. The idea is interact with the environment, push the accessibility buttons, get to the Starbucks, pick up your drink, and come back home. Now, this is a 4x video. I sped it up. It takes about 8 minutes for him to do this. And then the stretch of distance that he needed to travel is not maybe 200 meters or so. And then one thing that you saw, caregiver assistance, 3, right? So, 3 times he needed help from somebody. Our goal is to take this as a goal. This is the current state of the art. This is what he can do right now. But then how can we now slice off time, right? Of course, everybody wants to get to his coffee or their coffee as quickly as possible. And with the goal of making this 0, right? So caregiver assistance, can we provide full assistance? I had this long vision of, bringing individuals with disabilities through the metro station, metro system to wherever they want to go. So this will unlock, this funding will unlock that vision. My group specifically, this is a very large organization, very large team. There are 8 institutions, 5 universities, 3 companies. Companies will handle the tech development and hardware while we work on the algorithms. My team will specifically look at indoor and outdoor navigation. But then how can you provide safeties, right? So, safety is critical, especially if you're on a sidewalk. How do you make sure that, your wheelchair does not go over the curb, et cetera, et cetera. So, and then this is where the embodied AI piece will come into picture because, you have to wrap around something that can be repeatable. I'm going to pass this. This is prior work. And then we have a ton of other work that supports this, but I also want to make sure that I have time for questions. I'll leave this here. If you ask the question, I'll tell you what I'm doing for Amazon. But other than this, I'll stop and we can come back to this. And then thank my, all students. So the upper pack, 14 of them graduated, and no one picked the industry. They picked academia. They're all industry. They're all working for the big AI companies, robotics companies these days. I still have about 9, 10 maybe 15 incomings active. we got a lot of funding from the government and industry, etc. So thank you.